Okay.
We're Team 9794 with Study XC. We're a rookie team from Rockville, Maryland. I'm Rashi. I'm in 9th grade. I'm the project manager and engineering notebook coordinator for our team. I also help build a robot.
I'm Ishan. I'm in 8th grade. I'm the hardware lead and the systems engineer who makes sure that the hardware and the software work together.
I'm Sartak. I'm an 8th grader and I'm a co-software lead.
I'm Vishal. I'm in 8th grade and I help work on the robot.
My name is Neil. I'm in 8th grade and I also help work on the robot.
We have 3 team members who cannot be here today due to the fact that they're taking the SATs. And then these are our team stars, Merlin and Vivian. We're from 6 different schools actually, and the way that we coordinated people from 6 different schools was through project management. We used a variety of online tools such as Ganter, Google Drive, email, and Google Hangouts to make sure everyone was on the same page. We had a lot of goals coming into this season. Our 2 main robot goals, which have a really cool autonomous program that was reproducible and paying. We also wanted to win a variety of judging awards such as Think, Innovate, and Control. So we worked really hard on our design process, going through multiple iterations. And here's our Control award sheet. But our main goal was to win Inspire, so we did a lot of outreach to the community.
So wrong.
From wrong, do we keep them?
Yes, but now we consider them good. So now we have to, yeah.
So, as mentioned before, one of our goals was to hang, and this involved climbing up the ramp, which is why we have 4-wheel drive. We have 4 AndyMark 60 motors controlling 4 individual AndyMark wheels. And at first we thought that the only way we could get up the ramp was with treads. And so we tried that, but we saw that this grip would actually latch itself into the churro. It wouldn't actually provide extra friction. It would just slip. And we tried multiple other things, such as adding these grips, but we saw that it was really bumpy and uncontrollable. So that's why when we found these AndyMark wheels, we saw that the entire wheel actually touches the surface, which gives us the friction. And an important thing to consider also while trying to climb the ramp was wheel spacing. So when one set of wheels was over the churro, the next was helping push the other set up. And so now we're able to climb the mountain.
So as the front wheels were actually falling over the second churro, the back wheels would actually come up and be pushed over the front churro, so then we could actually get into the mid zone, even using wheels.
Another thing we have to think about when climbing up the ramp is our center of force, or center of mass, sorry. And so most people, they would think about the center of mass of like our robot when it's on a flat surface, but as you know, we had to think about it when it was on an angle. And so we actually looked at force diagrams of our robot, and we decided to put most of the weight in the front of the robot, so that when we were on the incline, the center of mass would be in the center of the robot, so that it would equally distribute the weight to all 4 wheels, so that there was enough friction and traction for all 4 wheels.
We also have one of our goals was to hang, and we realized that we couldn't just use the drivetrain to get up and hang. So we started to brainstorm different solutions on how to grab onto that bar and pull ourselves up. One of the solutions was to use a tape measure winch. We tried out a rope winch where we connected a rope to the hanging bar and we reeled it in. And then we also had a solution of an arm. We decided to use the arm, and our arm features a rack and pinion, which allows us to pull up and grab onto the arm. And this rack and pinion actually can pull 20 kilograms, and we were able to calculate that using the Tetrix motor specs. So we went online and found those specs, and since we geared it 1 to 2, we were actually able to pull up 20 kilograms. Since our robot's only 10 kilograms, we can easily pull ourselves up into the high zone. But this wasn't enough, because since we have the pivot point of our arm so high, we would just be in the high zone. We wouldn't actually be hanging. So we decided that we need to actually collapse our robot on itself, so actually pivot the arm so then the robot would actually do a pull-up. And what we had to do is we had to actually gear the robot so then the angle that the arm moved on was powerful enough to actually lift the robot. And currently we use a 1 to 27 gear ratio, which is also able to pull up about 20 kilograms. And since our robot's only 10 kilograms, this works well. One of the problems that we had was that our robot would slowly drift down because there wasn't enough friction on the motor that would keep the robot out. So we tried out using a worm gear, since the worm gear doesn't allow backlash. But one of the problems with the Tetrix worm gear is you have to actually directly connect the axle to the worm gear. It has to actually spin the axle. And that would actually end up shearing the gear, shearing the axles, and creating divots in the on the flat parts because we had so much torque on them. So we went back to using a 1 to 27 gear ratio, and all of our axles are dead axles, so each gear is individually connected. The axles are just there as a support. And what we decided to do was we used these two clamps that were initially designed to get the all clear. They also acted to hold the robot up in the hanging position. Our robot also features many innovative features. So one innovative thing that we created was this flap. And we had problems with getting stuck on debris, and then our robot would be disabled for the rest of the match because our wheels wouldn't touch the ground. So we created this unique flap that we've never seen any team put on. And what it does is, so when it comes all the way up, it actually presses the switch, which acts as a limit switch. And we programmed it using a state machine, so then when it comes up, it can stay up, and we can actually get over the churros. Because if it was down, then it would press the churros and we wouldn't actually be able to get up.
So you did that for autonomous mainly, push debris out of the way so your
Yeah.
robot doesn't hit something.
Yes.
Yeah, even in teleop, it makes it easier for the driver to control it.
Right.
And then we also use our sensors in many unique ways in autonomous.
So, as previously mentioned, we wanted to have a great autonomous. To achieve our goals, we go forward to drop the climbers in the bin, and we back up and then we climb to the mid zone. While climbing, we get the 2 zipline climbers also. Yeah, with our servo over here.
Okay.
To test our
Okay, so you hit them. Okay.
to test our programs, we use Vivian, our test bot. This way, the software team can test their programs while the robot team is still working on the robot, and the code can also adapt as the robot changes. In our autonomous, when we go straight, we use a gyro sensor to follow an angle,
It's located right here.
and depending on the angle, we use proportional control to adjust the motors to make sure we stay on that straight line. Right before we get to depositing the climbers, we have our ultrasonic sensor, which verifies the position of the robot. So if it's too far or too close, it adjusts the robot right before it drops them in.
One innovative thing that we did with the ultrasonic sensor was we actually tested out different types of ultrasonic sensors. You know, if you can pull up the graph. So this is a graph of different ultrasonic sensors that we tested out. We first tested a Sharp IR ultrasonic sensor, and this is the graph from there. You can see that on a flat surface, which is the orange, so like a piece of wood, it actually worked really well, and it didn't have many outliers, and it was very accurate. But when we tested it on a piece of Lexan, which is more like what the field is, since it's an IR sensor, it was not as accurate when coming into close ranges, which is what we were going to use it for. And so we couldn't actually use that one. So we also tested out the Lego one, which is the one that we currently have. You can see that there are many outliers, but there is a definite trend. So we decided that we could actually average this one. When actually reading the values, we could take an average of them, and we would probably get something along that line. And then we tried out a Maxbotics ultrasonic sensor, and that one just was all over the place. You can see that all the data points are everywhere. So there was just too much noise on it. So we decided on the Lego one.
And when we average our sensors, we throw out all the zeros and most of the outliers so that way we get a more accurate reading. In our autonomous, one of the most important turns for us is when we face the ramp to go up. We use proportional turning to do that. So we use our gyro sensor to get to the correct angle, and we use proportional control to slow down the motors as we get closer to the angle so we don't overshoot.
That's all for
Programmed all that in.
Yeah, so we have a method in our
Pre-programmed.
autonomous that, so as it gets closer, it'll slow down, and even if it overshoots, it'll come back. And we just do that for a certain amount of time so that it's straight on the ramp.
Are you utilizing any of that as a subroutine during teleop?
We're never on the ground during teleop.
So during teleop, we just stay on the ramp.
Unnecessary.
We don't actually ever go back onto the ground, so we didn't need the need for it.
Gotcha.
So also during teleop, we use state machines, which was also previously mentioned. So state machines is just a way that we can actually move stuff while doing other processes. So we wanted a button on our controller that would move this up while we could be able to do other things. And a state machine was the simplest way to do this. So what happens is there's 4 states in this. Can you get the controller ready? So one of them is it's going to be off. There's no power being applied to the motor and nothing being done. One of them is coming up. One of it is coming up, and that's going to be a state. So when we press the button, it's going to go into the up state. And then one of it is going to be stay up. So when this limit switch is pressed, it stops the up state and it goes into this state.
The power's also turned on.
And the power's turned off. But let's say it doesn't touch it, it'll pull it back up. So if it gets caught on something, it'll just come back up. And then one of the states is the down state, which eventually leads to the on state. there.
That's excellent.
In our teleop, we also tried to make the controls easier for the drivers and also to simplify them. So instead of using the joysticks to drive, we use buttons to just go forward and backward at constant speeds. And we also have toggles, so instead of having 2 buttons for things, we just have 1, which is much easier. And also to pivot our robots, we use the triggers, so it's also
It just pivots our constantly
it's simple.
And it reduces human error.
by a lot.
This is your first year.
This is
Yes,
our
this
first
is
year.
our first year.
You guys first year or the team's first year?
This is our
The team's
first
first
year.
year.
And our guys.
Yeah, and
Everybody's first year.
everybody's first year.
As mentioned before, we really wanted to win the Inspire Award. So we did a lot of outreach to connect with the community. Not just the first community, but just our community in general. We went to events such as the Maker Fair, Gibbs Elementary School, various fall festivals to inspire younger kids to start doing robotics. But probably our most influential event that we went to connect with the community was we went to an immigrant film festival to inspire people, just as the movie Underwater Dreams inspired people. And we had a panel there and we got to answer questions about our experience, and we really inspired a lot of people to start thinking about doing robotics.
We also connected with the first community in different occasions. So we've mentored many teams and we inspired them to continue on with the robotics. They've seen our robot and they thought that it was really cool. So we've mentored many FLL teams. We held our own coaches boot camp to train the next generation of First LEGO League coaches. So what we did was we created our own curriculum to teach the coaches. We actually got a sponsor that allowed us to use their space, and they've now gotten connected with the First community. And we went there and we taught our boot camp. We gave advice to coaches. We taught them how to program, and it was a day-long, 8-hour session, and they learned a lot from it.
Another thing that we did for outreach to the community was we got a lot of sponsors along the way, such as Launch Workspaces, who sponsored our coaches boot camp and gave us space to do it. And they're actually thinking about donating space to have a first STEM center now. There were many other sponsors that we got too that helped us along the way. And
we were also ambassadors for FTC. We went to many FRC events, FLL events, and we would bring in our robot or a robot at the time, and we would show them like kids drive it around, and it was great to see how inspired the little kids who would just come and be able to move the joysticks a little bit. They just loved it.
we also, at one of our qualifiers, we were aligned with a team from an underprivileged school, and they ended up getting a trophy that they would not have gotten otherwise. And that really inspired them to continue with robotics and inspired other kids at their school to start doing it because they came back with a trophy that they wouldn't have gotten otherwise.
Now, you guys didn't load programming in like the Matrix. I mean, where did you guys get experience in programming?
So 3 of us go to a magnet school. So
Okay.
we go to a computer science, math science magnet, and most of us also did First LEGO League. So we took a lot of the programming concepts from there and we applied
And some
them
of
to
our
FTC.
parents helped us learn Java as well, and we used YouTube videos to learn Java. We started over the summer learning that.
And we spent a lot of time in programming that time as well.
So we would actually use this. So while we were building, since it was our first year, we had to learn how to build. We would use Vivian in order to learn how to program while we were learning how to build.
And when we were programming it, instead of making one program, we had separate things. So separate chunks of it, like the proportional control in one, and then the ultrasonic sensor in a different part.
Right.
So we could test the individual ones and combine them.
Very smart.
And one thing that we want to leave you with is we are a rookie team, but we've come a long way since the beginning of the year, and we actually ended up placing first at all of our qualifying matches, and at Delaware State, we were part of the winning alliance. And we are able to do autonomous, and we can hang, and we can consistently score around 220 points.
Wow, that's excellent. Mind if I take a picture of your
Yeah.
robot?
And these are for you. These are our team
Thank you.
carabiners.
I like your little pins. Did you guys make those? Or?
Yeah,
we
we
made them.
hot glued them. Since there's an FLL team with us, they actually made these pins with us, and we hot glued them.
Lego pins. I like it.
It's just really easy.
Right. So you have all the information. You talked about it all already in your engineering.
Yes, and there are tabs for a
Okay,
lot
very
of
good.
Do you get into the 4 state machines in here?
Yes, we
Yes,
do.
everything is detailed
When,
there.
when we were actually designing our state machine, our coach actually taught us about how a state machine works. And we actually wrote out the state diagrams, which you can find in the control. There's a control.
There are sections for control.
Yeah,
look at that.
Yeah, but we actually diagrammed out each state and how it would get from state to state to state. So how would it get from the off state to the moving up state? How would it go from the moving up to the stay up state? And how would it go down?
Very nice.
So you stuck with the ultrasonic sensor from the NXT. Did you try the EV3 one or anything like
The
that?
EV3 one we found was uncompatible with the
Okay.
new
Okay.
with the module. So we tried out the 3 different sensors: the Sharp infrared, the Max Robotics ultrasonic, but we found that this one was the best for our purposes.
Especially because depending on what surface
Feeling the perimeter of the
Yeah,
field.
the perimeter
It's clear
of
like
the
Flex samples.
yeah, and that would affect some of the sensors.
Just take a look at it. Just
Yeah.
So you have all Andy marks.
Yeah, so we
And
use
you have all your rotation
We have
sensors obviously
Inmark
hooked up,
16 here.
right?
yeah we got encoders on every single motor.
Right.
And we used dead axles on all of our wheels to prevent, because we
right.
had problems with axle shearing at the beginning, and this just makes it a lot easier.
Yeah, this especially with a load like this, you like you're saying, you rotate
Yeah,
the set
when you
screw on
rotate
the
it,
axle.
there's so much torque that it's just
Yes.
gonna
It
create
actually,
divots.
it was so much that it actually bent one of the axles.
There was an axle that was
axle-
at like a 90-degree angle.
Actually, completely bent.
'Cause that's a lot of torque with
So
that
we
much
had to go
ratio.
all the way across on every single axle,
Yeah.
otherwise it wouldn't bend.
This is nice.
Very nice.
One new thing that we actually found out at the Delaware qualifier was static is a problem. And we ran into lots of static problems because when the robot was climbing up the ramp, it would build up static. And then when a piece, yeah, with the wheels spinning and everything. So we actually put duct tape on every single piece of the robot that touches the ramp. So
Just to
then
insulate it.
Just to
And we
ground it,
ground
right?
it, and we ground it
at the beginning of the match,
every
we
match as well.
ground it, and
Good idea.
then it's an insulator.
Well,
So
yeah,
then
with the rubber mat, rubber wheels.
Oh, there's plenty of.
Yeah,
There's a lot.
of
There's a lot. And that would
opportunity.
interfere. It would just shut things down.
Got that chain nice and tight.
yeah,
Wow,
we
that's,
didn't want it to slip.
you didn't bend any axle with that, right?
No, we're not bending the axle.
Okay, that's good. That's really nice. Very, very nice. Clean.
Cable ties.
Thank you. Yeah, we use this, the home cable types. We also use file holders. These actually work really nicely, and they're
Yeah,
like
the report cover, like
Yeah.
file
Yeah.
holders.
They
Yeah, we
actually
used a lot
work.
of those. They work really well.
That. Well, I could talk to you guys all day.
Yes, you-
but
I-
we need
yes.
to move you
We
along.
won't come talk to us later.
We will.
all right,
Very
Well,
good.
excellent.
Yes,
great.
Thank you.
Thank you.
Thank you for your time.
Thank you.
thank you.
Wait, wait.
We'll label our files when we get back to
Thank you again.
Thank you.
Yeah.
Wow. Holy smoke. I mean, my first year.
Thank you.
You got it.